while we were in the video. All right. So the first thing that I'd like to talk about is vectors and scalars. Remember, a scalar is something that just has a magnitude or a number value alone. And some examples would include temperature, mass, and time. Okay, so if something has a temperature of 30 degrees Celsius, that's a scalar. If something has a mass of 5 kilograms, scalar. Okay. On the other hand, a vector is something that has a direction and a number associated with it. So things that you would see in this class would be stuff like force, which we haven't talked about yet, but we will. Velocity, acceleration, displacement would also be vectors. So anything that has a number and a direction associated with it, that would be considered a vector. In lesson 3, I talk a little bit about that you can represent a vector with an arrow. And basically how it works is the length of the arrow is indicating the magnitude of the vector, how big it is, or how small it is, and the head of the arrow indicates the direction. So for instance, let's say I have two cars going at some velocity. I have car A and I have car B. Let's say this was the arrow representing car A, and this is the arrow representing car B. Which car is going faster just based upon the arrows? B, how did you know that? Very good. The length of this arrow is bigger, and so this one would be going faster relative to this one, which would be going slower. Notice there's no numbers associated with this. I can't tell you for certain what the velocity of car B is versus A, but I certainly can say A is slower than B. Okay? Hopefully you guys are okay with that. I'm going to scroll down this page a little bit. Adding vectors is something we'll do in a lot more detail later on. But for right now, basically, let's say, Darian, you play football, right? Yeah. Okay. Let's say Keno and Darian, they're pushing, or we'll say they're pulling against each other, okay, on like a tug of war. And here's Keno's force vector pulling left. Who's stronger? Okay, it's undetermined. I'm going to say here's Darian's force vector. So Keno plus Darian equals who's going to win this tug of war fight, just based upon my arrows. We don't really know. Maybe we can test this out later. Darian, right? How do you know? Well, his arrow's bigger, right? He has more force that he's applying to this rope than Keno is. Now, if I were to add those two vectors, if I were to add Keno plus Darian, what would the net result be? To the right or to the left? Right. Would the arrow be bigger or smaller than this arrow that Darian has? Good. We have to subtract Keno's force to it. So it'd be something like maybe like this. All right, and that'd be Darian. That's adding vectors. And we'll do a lot more with it later on once we get out of this chapter. But just right now, just realize you can kind of combine them together to get something. And this will be shown even in further detail in just a second here with this deer. So that's scalars and vectors. Let's talk about position, distance, and displacement. The distance an object travels is solely the amount of ground an object covers. Okay? It's a scalar quantity, and it's measured in meters in this class. So if you'd like to close your eyes as I read you a story, be my guest. On a sunny afternoon, a deer walks 1,300 meters east to a creek for a drink. The deer then walks 500 meters to the west to the berry patch for dinner, before running 300 meters west when startled by a loud raccoon. What distance did the deer travel? Wow, that's a good story. So if I were to calculate the distance of this deer, how would I do that? Add them all up. So I'm going to say 1,300 meters plus 500 meters plus 300 meters equals 2,100 meters. And that would be the distance this poor old deer traveled. Okay. Notice no direction is associated with this problem. We don't really care what direction the deer traveled. We just added them all up, and that was the total distance that deer traveled. Now, same story, but this time I'm wondering, what is the displacement of the deer? Okay, so this time I'm going to draw some arrows here. The deer walks 1,300 meters to the east, plus 500 meters to the west plus another 300 meters to the west. What is the deer's total displacement? And this is kind of like the tug-of-war problem that we had before with Darian and Kino. Well, I don't really add these per se. I would do more like 1,300 minus 500 minus 300. And so what would I get? 500 meters. And what would the net direction be? East. Very good. Don't forget that. If you forget that, I sadly have to take a point off because you forgot that displacement is a vector. Okay. All right. Cool beans. Cool beans. Let's take a look at speed and velocity. The average speed can be given by the symbol v. Sometimes I see s. It just kind of depends on what source you're looking at. But the formula for it is v equals distance, and I'm sorry, my handwriting's so poor on this thing, divided by time. Okay? That is the formula. So we have the same deer problem here. It goes for a drink, eats some berries, gets scared by a raccoon, and it says that what they want you to calculate the deer's average speed if the entire trip took 600 seconds. Okay? So what distance did the deer travel? Well, if we look at the front, I believe he traveled 2,100 meters. And how long did it take him to do that? Well, the problem tells us it took him 600 seconds. So if I do 2,100 divided by 600, I believe that gets me 3.5. And what would the units be on this? Good. Meters per second. Notice there isn't a direction associated with this because speed is a scalar quantity. Right? There's no direction at all. Now for velocity, which is a vector quantity, the formula is v equals displacement over time. Okay, notice the difference is instead of distance, we're using displacement. So if I do the same problem here, this deer gets a drink, eats some berries, gets scared, and it took still the same amount of time, what is his average velocity? Well, on the front of the sheet, we calculated that the displacement of this deer was 500 meters east, right? And I'm going to divide that by how long did it take him to travel 500 meters east? Well, it says in the problem 600 seconds, right? And so if I do 500 divided by 600, I believe that gets me 0.8 meters per second. And what else do I need to put it in there? Good. I am happy to hear people saying that. East. Don't forget that. Okay. And again, notice the difference here between speed and velocity. I mean, he has a much higher speed, 3.5 meters per second, but his velocity is actually only 0.8 meters per second because it's only based upon his displacement from his starting point. Okay, so don't let those things mess you up. All right. One last little thing I want to talk about, and that is acceleration. Acceleration is the rate at which velocity changes. And when you think of acceleration, think of the change in velocity. And the formula for it is A equals delta V over T. Or, if you prefer, delta V, another way of writing it is V final minus V initial over T. All right, so it looks something like that. Acceleration is a vector. The thing that throws a lot of students through loops is the acceleration can be directed in one direction, but your velocity will be going in the opposite direction. Remember, velocity explains the motion of an object, and acceleration just is talking about the change in velocity. It's not going to tell you the direction the object's moving always. Okay, so just kind of keep that in the back of your head. Down here I put some examples for you just to kind of ponder. This is an example of zero acceleration. A car traveling at 30 meters per second east. Oh, sorry, that went a little crazy. So basically, what they're saying is this car is going 30 meters per second east. It's just cruising at that velocity. There's no change in it. Okay, it's just going to go 30 meters per second. An example of a car with a positive velocity would be if it starts at rest. So let's say it's like at a stop and go light, and then the light turns green, and it accelerates in the positive direction or the east direction at 5 meters per second squared. So every second, the car is going to be going 5 meters per second faster. So after 3 seconds, how fast would that car be going? If it starts at 0, at 1 second, how fast would the car be going? Good. At 2 seconds, how fast would the car be going? Good. At 3 seconds, how fast would the car be going? 15. So 15 meters per second would be the speed of the car after 3 seconds if it keeps that constant acceleration. All right. An example of a negative acceleration, the car is going 15 meters per second east, and it accelerates at a rate of negative 5 meters per second squared. And that negative basically is the equivalent of saying in the opposite direction that it's traveling. Okay, so what does that mean is happening to the car? It's slowing down. All right, so after 2 seconds, what would the speed of the car be? Because when I ask a question, it's just completely silent. It hurts my heart. So the car is going at a velocity of 15 meters per second east, and it accelerates at a rate of negative 5 meters per second squared. How fast would the car be going after 2 seconds? 5 meters per second. What direction? East. East still. Okay. Notice the acceleration and the velocity can be in completely opposite directions. The velocity explains the motion of the object. The acceleration explains how the velocity is changing. Okay. That's a little confusing. Like that's how I can catch a lot of people on questions that you lose points on. So hopefully that helps you a little bit. Maybe not at all.